scale in simulated environments using ecological modeling and isotope technique. So moving to the problematic, as we all know, the agricultural sector uses over 87% of available fresh water with low efficiency that doesn't even exceed 15%, which is a great problem. We have other economic sectors just like urbanization, industry, tourism that have also an impact on the water resources. We can note also that the climate change effects are expected to decrease water availability, particularly in our regions, the NENA regions. And in order to deal with the food security problem, the irrigation must be intensified to feed a growing population, mainly through the groundwater resources, which are already under threat from overexploitation. So, knowing all these facts, let us trigger us to think about a way to understand all these processes and evaluate the irrigation water policies, and that by developing a new strategy for sustainable management of water resources. So to do that, we have to deal with a big question, which is how do we maintain a sufficient, efficient, and sustainable agriculture without affecting water resources? So the thesis which I work on is part of a project funded by OCP, which is ASTUAT. That stands for Assessment of Sustainable Irrigation, water scarce regions using remote sensing and hydrological modeling, which aims to develop a decision support system that incorporates models, methods, climate projections, agricultural practices, and they're going to be useful for the end users, such as just like agriculturers, national authorities, in order to have a better sustainable water resource management. So, as I said, the DSS incorporate live models and methods, where my thesis is interested in the estimation of the groundwater recharge, which is a very complex process, and is when the waters moves downwards from the surface water to groundwater, and has been proven very hard to assess. So we have multiple methods to estimate groundwater recharge, mainly the hydrological models, just like, for example, physical process-based models, physical models, and we got chemically based models that uses conservative tracers, just like isotopes and chlorides. And for the data needed, we might need remote sensing products, reanalysis, in situ measurement from ecovariance towers, scintillometer, lysimeter, meteorological station, etc. Okay, so our target area is the house plane, which is part of the Transvaal. I guess my colleagues yesterday, most of them work on the same the region. So why this particular region? Because it's well instrumented. It has been on survey since 2003, and it suffers a lot from the climate change. Some characteristics of the study site is a flat plan with a high evapotranspiration rate that reaches the 1600 millimeter per year. We've got different type of irrigation methods, drip irrigation, flood irrigation. We've got multiple crop types and different areas, type areas, private area, modern areas, traditional areas. Okay, so my main objective of this first work is trying to assess the groundwater recharge in the agricultural plot scale. So I tried to divide this into a specific task, starting with the simulation of different water and energy fluxes, moving to the sensitivity analysis, and finally ending with the calibration and validation of the different outputs. So, what model to use? I think the model I presented here two types of hydrological models because they are the main one used in research. So, choosing the right model that fits our interest, feasible with the problematics, data availability, and methodology. So we've got hydrological models that impose many assumptions, especially in groundwater, representative area values, numerical equations, etc. We have distributed physically based models, which incorporate more than just water fluxes. It can be also have another fluxes, just like energy fluxes, phenological fluxes, and it can analyze the hydrological response at ecological basins. So our model was the EcoISO, which is a process-based model developed in the University of Montana in 2013. It can be applicable to all sizes, starting from plot scale to an entire watershed. It incorporates three balances: energy balance, water balance, and plant phenology balance. So it computed all the water fluxes that can be representative, such like stream discharge, evapotranspiration, the partitioning of evapotranspiration, which means evaporation and transpiration, groundwater recharge, snow melting if we are in a snow-covered area, and yeah, the model is customized onto three layers. The first layer is going from 0 to 10 centimeters, which is the evaporative layer. The second layer is the root layer, going from 10 to 15 centimeters. And finally, the unsaturated zone that goes beyond to the aquifer. And another feature of the model EcoISO is that we can add conservative tracers like isotopes in order to quantify water ages and track the origin of water from the precipitation to the groundwater. So these are the main model equations. So I changed the colors because we have, like I said, three budget. For the energy budget, we have two equations. Water budget, 3, and phenological budget, we have 2. So our first start was on the F3 location in a winter wheat plot with a soil clay to loamy with a fluid irrigation system. And here are our first input. So the model uses as input relative humidity, temperature, precipitation, wind complement, short wave radiation, long wave radiation. You can see that we have some gaps. So we tried to fill the gaps with air fiber analysis, and the results were not bad. We tried to compare the two methods. We only had an overestimation of precipitation. So we worked on 4 years, going from 2010 to 2014. You can see that I've tried to give a detail on one hydrological year. For the precipitation, you can see that there are like 4 or 5 peaks that are strangely higher than the normal, because it's not precipitation, it's the irrigation events. So the models consider irrigation events as part of the precipitation. So we got 4 to 5 episodes of irrigation, like the graph in yellow. The data used for calibration, using the methodology, using the eddy covariance data, the dosimeter, and the TDR for computing the for quantifying the volumetric water content. So here our first trial. These are the energy fluxes, latent heat flux, sensible heat flux, net radiation. You can see that they are not fitting at all. So we wanted to make it more realistic, so we went through a calibration, but before doing that, a sensitivity analysis must be performed. So after doing a sensitivity analysis on both power budget and energy budget, we spotted that for the water budget, we've got the Brooks and Curry coefficient, which related to porosity as well. We've got the water content coefficient and the roots, the coefficient of root exponentials. For the energy budget, there is the Cabris, which is the coefficient of light extension, and optimal temperature. So these were the most influencing parameters, which can make the task easy for the calibration. So after the calibration, here's what we got. For the soil water content, the first and the second layer, well, the second layer looks very good. The first one not bad, but the third one not at all, because we didn't have any measures beyond 15 centimeters. For the energy fluxes, the latent heat flux, the net radiation, and the sensible heat were not that bad and require more enhancing. So here's what the model can output from the evapotranspiration, where we can partition the evapotranspiration into evaporation and transpiration. And our main goal is the estimation of groundwater recharge. We can see that the peaks match perfectly with the irrigation events. Not perfectly, but we can have like a delayed time. It's the time consumed by the water to go through the layers to reach out the aquifer. So the next step we are developing now is to develop an isotope sampling protocol by analyzing the isotopic signature in aquifer, in the plants, in the soil, and the rain. And in order to have a more robust estimate of aquifer recharge by predicting water ages in soil store and recharge fluxes. Thank you.